recording. I welcome you for the week 8 live interactive session for the course Polymers, Concepts, Properties, Uses and Sustainability. Okay, now let's get on to the session. I'm just sharing my screen. Hope you are able to see my screen now. I need some reply, please. See, you can very well unmute and speak. Okay. Uh, if you do not have any problem with your mic or something, you can you have to actually unmute and speak. For example, you may have to answer the questions, and you can also post your queries, and that is what is the purpose of this session. Okay. So please try to unmute and speak as much as possible, and don't hesitate. Whether the answer is right or wrong. Okay. End of the day, we are going to learn. Okay. So now let's get on to the session. As usual, we'll have a brief recap of lectures of week 8. So, week 8, there was a discussion on viscoelasticity in polymers. So, lecture 53 was on testing for application. So, this was a lecture on uses. Okay. So, measurement of properties for a given application. So, here in this lecture, there was a discussion on trade test basically. So, what are the examples of a trade test and what are the features of a trade test? Uh, is it fine? Can I continue?
Yes.
Okay, fine. Now you're able to speak. Good. I welcome you to the session. Now let's continue with the brief recap of lectures of week 8. So, as I was discussing, so lecture 53, there was a discussion on what are the examples of trade test, what are the features of trade test. So, trade test mostly it gives some numbers. Okay, it does not really give the material property, but it gives some numbers, to get an idea on certain properties or certain, behavior depending on application. So one trade test, for example, that was discussed in the lecture was on hardness. So different hardness testing were discussed, and if you could remember, these hardness testing methods, they had the values between 1 and 100 to give an idea on hardness of the material being tested. Okay, and what are the different methods of testing was also discussed, and there was a short discussion on volume and surface resistivity, right? So polymers in general, they are insulating materials, but the concept of surface resistivity plays in a role because obviously any material, it is going to interact with some surface. So for example, inherently the polymer might not have any kind of a conductivity, but due to this presence of certain materials, like for example a dust, or some other material that gets accumulated in the surface, or even for example a crack developed and then accumulation of some materials in the surface, what happens is that the resistivity and the conductivity might change. So that is why you bring in the concept of the surface resistivity, and the relation between surface and volume resistivity for practical appreciation was also discussed in this lecture. Hope you are able to recollect. Are you able to recollect anything?
Ma'am, I am audible.
You're audible. Yeah, I'm asking whether you're able to recollect, when you went through the lectures, uh, these concepts were all discussed. So, are you able to recollect those concepts?
No.
Okay. Did you go through the lecture?
Yeah, yeah.
Okay. Okay. So in hardness, different hardness testers like Shore hardness, Shodi, and then, for example, Rockwell hardness. This was all discussed. Okay. And even, kind of an optical property. Also, what is the trade test and what is, kind of a material property. So these aspects were actually discussed in the lecture. Okay, and then lecture 54 was on properties of blends. Okay, here first of all, there was a discussion on the property of a particular property, a modulus of a polymer, a pure polymer, and a blend, based on its glass transition temperature. How does the behavior change? So temperature versus your E prime curve, plot was shown for a two pure polymers, one having a lower glass transition temperature and one having a higher glass transition temperature, and how is the modulus behavior for each of these individually, and also when when they form a miscible blend, how is the behavior, and when they form an immiscible blend or a partial miscible blend, how is the behavior. So these were all discussed. Okay, and uh, yeah, for example, uh, when there's a glass transition temperature, there's a step change in the behavior, or you can see a significant change in the modulus in the behavior for a pure polymers. Okay, in their glass transition. If it is a miscible blend, then the miscible blend, it will show that kind of a change, a step change in the material behavior somewhere in the temperature in between your individual polymers glass transition temperature. So that is what was discussed. Okay, and then in case of blends, so you're blending two different materials. So the effect of the property change may be an additive, which can be like for example, if a modulus is 5 pascals for one material and 10 pascal for the other material. Okay, depending on the concentration, it can be a linear relationship when you add in a blend form, or there can be cases where the material can have the final property in a blend form which is much higher than the individual polymers properties. Okay, that is what is the synergistic effect. And there can be sometimes a negative effect also, where when you blend two polymers, the property can actually decrease also. So these, kind of possibilities were all discussed. And then how was toughening done using rubber particles? And how does, your properties like your impact strength uh, changes when rubber particle is added, was discussed. And then blends of conducting polymers. So there was a discussion on conducting polymers in one of the earlier lectures, right? There was a discussion on conducting polymers like polyaniline and then P dot PSS, right? Where they are conjugated polymers, they have alternating double bond and single bond and all. So there was that discussion. So uh, what was discussed in this lecture of blends of conducting polymers is that we need not have the pure conducting polymer. For example, if we have pani as pure, it may be a conducting polymer, but it may not be, you cannot form a kind of a flexible film with that. So you may need to add some other polymer to improve some mechanical properties, but still you can have a good conductivity when you have a blend also. In fact, in the lecture it was discussed, in case of a pani system, for particular combinations, even if you add like 30% zero point 0.3 volume fraction of pani, you can have a percolation, and there can be multiple fold increase in the conductivity from a insulating zone to a a semi-conducting zone, right? That was discussed in that lecture. Okay, you're able to follow. Don't worry if you're not able to follow, at least just get on to the points that these things were discussed, so that when you go back and see the lectures, you will get much more idea. Fine. Next, in the lecture 55, there was a discussion on biomimetic polymers. Okay, this was on sustainability aspect of the course. So biomimetic devices and materials were discussed. Okay, and then biomimetic polymers examples in lubrication was discussed. And then can there was question posed that can polymers be developed which mimic materials in biological organisms? Okay, here in this, the hierarchical structure of collagen was discussed in detail, and its properties were all discussed. The importance of hierarchical structure and all was discussed, and a thought process was brought in, whether this kind of a structural aspect can be brought in and mimicked in the other materials as well to bring in a similar property as that of collagen. Okay, so these were all discussed in the biomimetic polymers lecture. Hope you are able to follow. Once again, let me see my recording. Yeah, it's getting recorded. Next up, lecture 56 was on advanced mechanics. Okay, this was on properties again. So, phenomenological description of mechanical response was discussed. Here, idea of mechanical analogs was given, and what is the basis of an overall model. So, different mechanical elements for different aspects, like for elasticity, plasticity, and viscous behavior. Different mechanical analogs were discussed, and then for a particular polymeric behavior, whether these kind of analogs can be connected in series or should be connected in should it be connected in parallel, and how many of these springs should be there, how many of these uh, you know uh, dashboards should be there, so that you could model the actual polymer behavior. So these aspects were discussed. Okay, mechanical analogs is nothing but you have your resistors and all, you could imagine, right, in uh, electrical analogs. So similarly, for mechanical behavior also you have a mechanical analog. Okay, and then the concept of failure in materials was discussed. Here, Griffith's hypothesis was discussed in detail, and then different crack growth mechanisms. So, what are the crack growth mechanism in case of thermoplastics and in case of thermosets? What is the crack growth mechanisms in case of rubbers? So, these were all discussed in depth. Okay, that is, what are the different mechanisms. You were given an idea on these mechanisms. Okay, and then fatigue was discussed, and then the lecture was closed with a summary of the mechanical response. So all the all the possible types of mechanical response of a polymeric structure, where there are certain set of mechanical responses, like your elastic response, or your viscous response, or your plastic response, a viscoelastic response, linear viscoelastic response. Uh, so these are all the responses where you see some structural changes in the polymer, but it does not cause the material to fail or fracture. Okay, fail. Okay, but in case of, there are certain responses where you could see that the material is failing. For example, in case of an impact, or in case of a fatigue. Okay, or in case of a fracture and all, uh, you could see the material actually failing. Okay, so these were all discussed and summarized. Next, lecture 57 was on viscoelastic response examples. So here, master curve was explained in detail. So in previous week lecture, there was a discussion on time temperature superposition. So this is in line with that, where you prepare master curves. So how do you prepare master curves? So you can based on the time temperature superpositions, you can prepare master curves, because for example, a polymer can have a service life of 25 years, right? So you have to know how's for example, your compliance, creep compliance for 25 years. But in actual practical scenario, you cannot keep conducting tests for 25 years, and after 25 years you can say that this material is having a 25 years compliance, or it does not have that much of a compliance to withstand for 25 years and all. So you cannot, you in practical purpose, you do not have the actual that long time. So what do you do in reality is that either you provide some stringent conditions. One of the most common stringent condition is your temperature. So uh, you could do some testings at very low temperatures and at very light high temperatures, and based on time temperature superposition principles, you can produce master curves, so that you will have the time data for 25 years, even though you do not actually do the test for 25 years. So that is what is a master curves that was explained. And then dielectric response of polyvinyl alcohol at different temperatures was discussed. Okay, where at very low temperatures, it gives some residual dielectric response only, because it is not able to, the poles, dipoles are not able to orient. Whereas at sufficiently high temperatures, the dipoles are able to orient. Okay, and also there is a function of frequency as well. Okay, and then viscoelasticity, relaxation time and different measurements was discussed. Okay, though relaxation times, it varied for different type of measurements, for a dielectric spectroscopy to that of a mechanical response, but the overall behavior was very similar. Okay, with respect to temperature, right? Are you there? I just request you to respond something, because when I go to the PPT mode, I will not be knowing whether I'm connected or not. Okay. So once in a while, say that yes, you're able to follow, you're not able to follow, or you're connected or something. Okay. Next. So the next set of lectures were on interaction of polymers with other materials. So lecture 58 was on polymer packaging. So do we use polymers for packaging? Do we use polymers for packaging? Packing something, do we use polymers? You can unmute and reply, or you can just type in the chat box. Prem Kumar, are you connected?
Yes, yes.
Okay, you
I'm
can just
connected.
unmute and reply. Okay, when I'm asking
Mm,
some questions and all, no, don't hesitate to answer. Okay,
This time I'm driving. This time I'm driving, so
okay,
I'm
okay,
sitting and listening.
okay. No issues, no issues, no
Okay,
issues.
okay,
Okay, no
okay,
issues. Yeah. So polymers are used in packaging applications. Okay, they are very widely used.
okay,
So these
okay,
applications, can in packaging applications, the purpose of their use can be as a barrier films. For example, in your chips packet, you have your polymer. It's covered in a polymer package, right? So your chips, when you open the chips packet, the chips should be crispy, right? So that means this packaging should not allow moisture to pass through or oxygen to pass through and react. So if moisture passes through inside the packaging into the chips, what happens? The chips become soggy. Okay, you will not have the chips very crisp. So it should act as a barrier for moisture. So these are the barrier properties. Similarly, it should have impact resistance. For example, when you're packing some glasses and all, you may pack it filled with styrofoams and all, because they are very brittle, right? Glasses are very brittle. Sometimes you will have beautiful art pieces of glasses. So if you just pack it normally, it may break. So it should be covered with a proper impact resistance, so that while transport and all, it should not get affected and broken, your the product you what you want. So it should have that kind of a packaging, should have an impact resistant packaging. So there can be polymer usage as a secondary packaging as well. Secondary packaging means it need not have any barrier properties or impact resistant properties, but something like your aesthetic, or something you want to print on that. So you may not be able to print on the actual product, but you can print some information on the packaging. So for having a printability. And then electronic packaging. So electronic components, in any components you take, for example, your mobile phone, it is having polymers, right? Your back side is made up for polymer, right? And your components are also separated, with different polymers, and there can be some portions of conducting polymers as well. Okay. uh, so this is what is the role in electronic packaging. And what about, so when polymers are extensively used in packaging, then we have to think of the renewability also. Many cases, your polythene, which you are using for packaging and all, no, becomes an issue, right? So you have to bring in your renewable aspects, biodegradability aspects. So some biopolymers like starch or cellulose can be used in combination with the synthetic polymers, or as standalone also for packaging. So those researches are going on, and there are some practical applications as well. So these thought processes were discussed. Then what are the important phenomena associated with barrier films? As I discussed, and it was discussed in the lecture. So polymers, for particular applications. For example, if you are using it for food packaging and all, it should know it should act as a barrier against moisture or oxygen diffusion, right? So so the concepts of diffusion, absorption, adsorption, right? Leaching is another problem. So materials should, for example, the polymer, it may have some small molecules like plasticizers. So this plasticizers should not interact with your food material and leach into the food material. If it gets into the food material, it may be carcinogenic in nature. So it will affect your health. So it should not leach out of polymer also. Similarly, your gases or moisture and all, no, it should not enter from the environment into the packaging also. So these phenomena are important to understand if you are going to use polymers in packaging. Next is permeation. And then what are the properties of interest? What are the thermodynamic properties, like your phase equilibria, right? What are the transport properties, like your diffusion, permeation? So these were all discussed. And then permeation was discussed in detail, and permeation rate for packaging materials was also discussed in detail in the lecture. The next lecture was on porous polymers or membranes. So, polymeric separation membrane mechanisms. So, what are the different mechanisms by which small molecules diffuse through the polymeric membranes? Solution diffusion mechanism, Knudsen diffusion, molecular sieve. So, the polymeric membranes can also act as molecular sieve. That is, in mechanical sieving, you could have seen, even at home you could have seen that it sieves off larger particles, and only smaller particles pass through that particular sieve. Similarly, in molecular sieve, the molecules, the pores are of very small size, that the larger molecules which you want to avoid, you ensure that the pore size is smaller than the molecule which you want to avoid. For example, oxygen you want to avoid from passing through means you design a polymer with the pore size having smaller size than the molecular size of oxygen, so that the oxygen molecule does not pass through and it acts as sieve for oxygen molecule. That is why it is called as molecular sieve. So this was discussed. And then miscibility processing to make porous membrane was discussed. And then there was a discussion on polymeric foams, different types of polymeric foams. For example, open cell foam, closed cell foam, and then distribution of force. Okay. And then whether it can be a uniform distribution, or it can be a non-uniform distribution also, right? More pores concentrated in one area, whereas in other area there are less number of pores or no pores also. And how do you actually bring in, either by a single processing, or you can create sandwich structures as well. And phase separation between your polymer and your gas phase. So what are the blowing agents used? The blowing agents can be of two types. It can be of a physical blowing agent. That means a direct gas molecule like your carbon dioxide or nitrogen can be brought in inside along with your polymer, and then when they escape, actually the escape zone forms the pores. Or there can be chemical blowing agents, where the direct gas molecules are not added, but due to certain chemical reactions under processing condition, polymer processing conditions, these molecules react and create gases, like your nitrogen is released, or carbon dioxide is released. In fact, in one of the earlier assignments, azocarbamide was discussed. This azocarbamide, carbonamide, it acts as a blowing agent by releasing different gases like nitrogen and your carbon dioxide and all. Okay. uh, and acts as a blowing agent. Okay, when these gases escapes, your pores are formed and foams are formed. And then what are the examples of polymeric foams? So the common examples are your polyurethane, your styrofoam, polystyrene, polypropylene can also be used to prepare polymeric foams also. So these were all discussed in that lecture. Next, lecture 60 was on polymers at interfaces. Okay, so this was a concept based lectures. So interfaces in polymeric systems. What are the different interfaces? What are the different interfaces that does a polymer actually interact with uh, during its service or during processing? Okay, For example, it gets exposed to environment, so there can be an interface between polymer and the environment. Or during processing, the polymer melt can have an interface with that of the instrument surface. Okay, polymer solutions, solvent and the polymer, there can be an interface, right? And interfaces formed in different polymeric systems. For example, in case of blends, and in case of polymer composites, there can be an interface between the polymer layer and the fiber layer, and there can be an interface between polymer blends between two polymers. There can be an interface formed, and in case of multi-layer polymers or joint products as well. Okay, and a difference between the bulk polymer and the polymeric interface behavior, how the behavior changes in an interface. And then uh, a question was brought in macromolecules in thin films. So if it is a very thin film of macromolecule, then you do not have a surface bulk polymer at all. Everything, it will be exposed to it is having an interface, right? So confined macromolecules in confined spaces was discussed, which has a huge practical applications, right? And then surface energy of polymers. So here surface and interfacial energy of polymers were discussed, and then the contact angle was discussed, surface tension was discussed, and then how do you manipulate the surface energy or interfacial energy in polymers. So these were all discussed in polymers at interfaces. Next, the final lecture of the week was on diffusion in polymers. This was again a property based lecture. Okay, so fixed law of diffusion and diffusion of water through different substances, like diffusion of water through air, water vapor through air, diffusion of water vapor through water ethanol system or through a quartz. So these were all discussed. And then how is the diffusion in liquids and solids are. For example, in liquids, the diffusion is based on the Brownian motion, which has a Stokes-Einstein relation. Whereas in case of solids, you have a hopping of the small molecules through the crystal lattice. So this hopping is very similar to your random steps. They have a random steps, which is very similar to your random walk model in your macromolecules, right? And how is the variation with temperature, the diffusion of a liquid and crystalline solids. And then so basic liquids and solids were discussed. Now our ultimate aim is to understand diffusion in polymers. So the free volume and diffusion of small macromolecules in polymers was discussed. So how the diffusion happens. So it is a combination of activated and a free volume diffusion process. And then how is diffusion in an amorphous form polymer different from a semicrystalline polymer? So what are the other parameters is a crystallinity in polymer brings in for diffusion of small molecules. So these were all discussed in this lecture. Hope you are able to follow. Uh, so now actually let's get on to practice assignment for week 8. So let's see what is the first question is. The following figure shows scales of hardness for different class of materials. Okay, so this is a trade test. They have shown the scales of hardness of trade test of hardness, the Shorey, Shorty, and Rockwell test for elastomers, thermoplastics, thermosets, and thermoplastic elastomers. Okay. Now the question is, you have to state true or false for the following statements. The first question is, the higher the number on the scales imply higher hardness. Is it true? If the number is 90 or 100, the hardness is higher. Is it true? Uh, are you in a position to type the answer, or you may not be able to type? I think you are driving, right? You may not be able to type or speak, I guess. Or you can just give a try. I don't know, because it's very risky if you're driving.
Yeah, ma'am. I'm audible.
Yeah, you're audible. I just want to know, will you be able to answer?
Okay, okay, okay.
Because you're driving, you said, so I just want to know. Otherwise, I'll just say the answers as well.
Okay.
If you find it difficult, because since you're driving, I don't want to take that risk. Okay, in fact, it's better not to attend the class when you're driving and all. So if you are actually driving, don't because your focus gets shifted between things. But still, of course, when you're driving, you listen to music and all. Similarly, you can listen to class and all, nothing wrong also. Okay,
Okay.
but yeah,
Okay, okay.
yeah.
Next time.
Yeah, next time, preferably, if you want to have a better concentration, since it is a live session, because this is an opportunity where you can ask so many doubts also. Okay, and if you're not able to understand, you can ask doubts. Okay, and also you can try attempting answering questions also. So try making it possible that you're focused in a particular place and listening. At least you don't do something risky. Okay, that's it.
Okay, ma'am. Okay.
Yeah. Okay. Anyway, I'll just go through the questions. You can just listen. Okay. Since you're driving, I don't want you to take risk on that aspect. Okay. So higher numbers on the scales means higher hardness. It's a true statement. So if the value is 90 or 100, that means, for example, in a Shorey scale, it means it is having a higher hardness. That particular type of material is having a higher hardness. The second question is, elastomer of Shorey hardness of 30 has a higher modulus than elastomer with the Shorey hardness of 90. Is it true? So what have they given? They've given two elastomers. One of them, they are having a Shorey hardness of 30 and another one is having Shorey hardness of 90. So the question asked is whether the material having a Shorey hardness 30 will have higher modulus than uh, the material having Shorey hardness of 90. Is it true or false? The answer is actually false. Okay, a material having Shorey hardness of 30 will have a lower modulus than a material having Shorey hardness of 90. Though you will not get the actual material property of modulus through a hardness test. Okay, it's just a number, but still it gives an idea on the material property also. So that means it is having a hardness of 30 will have a lower modulus. Okay, so these are the answers for the first question. Now let's get on to the second question. For mechanical analog elements in parallel, dash is equal. So there was a discussion on mechanical analogs. So spring, dashpot, and plastic elements and all. Spring element for elastic, uh, dashpot element for viscous, and plastic element and all. Okay. Uh, so when these elements are arranged in parallel, which is equal? Is it the stress that is equal or strain? Or is it stress as well as strain are considered equal when the elements are in parallel? Or neither stress nor strain are equal between these elements when they are arranged in parallel? The answer is actually the strain is considered to be equal when these elements are arranged in parallel. So if you look into this image, so uh, this 1, 2, and 3. In 1, you have a dashboard and a spring. In 2, you have a spring. And 3, you have again a sliding element and a spring. Okay. So 1, you consider this is one system, 2, second system, and third. So these are all arranged in parallel. So the overall strain, right, will be equal. Okay. So E1 will be equal to E2 will be equal to E3. Whereas when the elements are arranged in series, for example, this dashboard and spring, it will have a same stress. Okay, they take up the load equally. Whereas the amount of strain will be different in this dashboard and in this spring. Okay, so sigma A is equal to sigma B. Okay, in this case, if there's a series arrangement, and in parallel arrangement, the strain is equal, E1 is equal to E2 is equal to E3. Okay. Next, in Knudsen diffusion, which of these following statements are the right statement with respect to Knudsen diffusion? Is it pore size is very large compared to molecular mean free path, or pore size is very small compared to molecular mean free path, or pore size is of the order of molecular mean free path, or correlation of pore size and molecular mean free path is irrelevant? There is no relevance between pore size and molecular mean free path when you consider Knudsen diffusion. Which of these statement is correct with respect to Knudsen diffusion? So molecular mean free path is nothing but when you take a molecule, so set of molecules, so the path covered by the molecule before it collides with another molecule is called as a molecular mean free path. Okay. So in case of Knudsen diffusion, what happens is that the pore size is of the order of molecular mean free path. That means the size of the pore of the system, for example, a polymeric membrane has pore size which is similar to that of the molecular mean free path of the small molecule that is going to pass through that membrane. Okay. Why is this so? Is that this is to ensure that the molecule, it collides more with the pore walls and then diffuse through the system than it collides with the another molecule. Okay. That is why in Knudsen diffusion, the pore size is of the order of the molecular mean free path. Okay. So what happens if the pore size is very large compared to your molecular mean free path? So if it is very large, the pore size is very large. If it is a very large pore, then there will be more of particle-particle collision than uh, you know your particle-pore collision, and that becomes more like a bulk diffusion, and it's not Knudsen diffusion. Okay. Hope you got an idea. Next up, identify the correct statement according to Griffith's hypothesis. So, the rate of stored elastic energy decrease is greater than or equal to the rate at which surface energy is created during crack growth, or the rate at which surface energy is created during crack growth is greater than or equal to rate of stored elastic energy decrease, or is it the rate of stored elastic energy decrease is equal to the rate at which surface energy is created, or no, the rate of stored elastic energy increase is greater than or equal to the rate at which surface energy is created during crack growth. Okay. Uh, so the answer for this is the rate of stored elastic energy decrease is greater than or equal to the rate at which surface energy is created during crack growth. So Griffith's hypothesis is basically for elastic materials. Okay. So elastic materials, because of yeah, because of their positions, atomic positions and all, they have some stored elastic energy. Okay. When a crack is growing, so these atoms are getting separated. Okay. So this atoms, when the crack surface has to grow and the separation between atoms has to take place, then this elastic energy stored should be taken up. Okay. The rate at which the elastic energy starts decreasing should be greater than or equal to the rate at which the surface energy is created, because when your crack is the crack is formed, there's a surface that is created. So when a surface is created, there's an energy associated with it. So as a crack starts propagating, what should be the case is that the stored elastic energy decrease. Okay. Obviously when the crack starts forming, there will be an elastic energy decrease. Okay. Because there is a law of conservation of energy. So the elastic energy decrease, the rate at which the elastic energy decrease is happening should be much greater than the rate at which a energy is created due to the crack growth. Then only the crack starts propagating and it starts increasing in size. Okay. Now let's go on to the next question. Phenomenon of polymers undergoing plastic or viscoelastic deformation till failure. During a cyclic loading, usually less than the strength of the polymer. Is, is it fracture, or is it impact, or is it fatigue, or is it plasticity? So, polymer is undergoing some cyclic loading. So, during the loading and unloading, there will be some elastic and plastic deformation. But eventually, the material is failing. So, this cyclic loading, that is, it is loaded and unloaded, loaded and unloaded. So, loading and unloading until failure. This phenomenon is actually called as fatigue. Okay. Next, the number of cycles to failure dash with increase in stress amplitude. So does it increases or does it decreases, or is it independent of stress amplitude, or it increases initially and then decrease? Which of these is the right relationship? Hope you're there. So it's actually the number of cycles to failure in case of fatigue. It decreases with increase in stress amplitude. Okay, this is actually called as an endurance limit. Okay, if the stress amplitude, the applied stress is very high, then the number of loading and unloading cycles will be very small for the material to fail. Whereas if the stress amplitude, the stress applied on the material is very small, then it can have, uh, more number of loading cycles. For example, if you apply very high stress of like say gigapascal, the number of cycles for failures might be 5 or 10. But if you apply 1 pascal, then you may have hundreds of cycles till the material fails. Okay. Now next question. In solution diffusion mechanism, for a higher permeability, which of these should be there? Should it have diffusion coefficient higher as well as solubility lower, or should it have diffusion coefficient lower and solubility also lower, or should it have diffusion coefficient uh, lower and solubility higher, or both diffusion coefficient and solubility should be higher? Which of these is right when you should have a higher permeability? Okay, diffusion coefficient is nothing but something that says about a diffusion of a material through another material. Okay, similarly solubility is a parameter that determines the solubility level of a material A in material B. Okay, so which of these should be higher to have a higher permeability in case of solution diffusion? Hope you're connected. Prem Kumar, are you there? Okay, I see you got disconnected. Maybe that's fine. So in case of solution diffusion, the permeability will be high if both diffusion coefficient and solubility are higher. Okay, permeability has a direct relationship, that is, it is directly proportional to the diffusion coefficient and solubility. So you could see that permeability is equal to diffusion coefficient into solubility. Okay, next, interstitial C is defined as, how is interstitial C defined? Is it lattice atom displaces diffusing atom to an interstitial position, or diffusing atom displaces lattice atom from interstitial position to a lattice position and then it occupies the interstitial position, or diffusing atom displaces lattice atom from the lattice position to an interstitial position and then it occupies the lattice position? Which of these is right in terms of interstitial C? So the right answer is, in interstitial C, the diffusing atom, it actually displaces the lattice atom from its lattice position to an interstitial position, and the the diffusing atom, it actually occupies the lattice position. Okay, next, Both liquid type diffusion coefficient and solid type diffusion coefficient have similar type of relation with temperature. Is it true or false? So it's actually false. So diffusion coefficient in liquids, is based on Stokes-Einstein relation, where diffusion coefficient is directly proportional to the temperature, whereas in case of diffusion in crystalline solids, the diffusion coefficient has a Arrhenius relationship with the temperature. Okay, uh, we already saw in the brief recap of lecture, and in lecture it was discussed that there is a hopping mechanism and it has to cross some barrier energy. Okay, it has a Arrhenius relationship with temperature. Okay, in case of solids. Next, diffusion in amorphous domains is impeded by obstacles in crystalline domain. Is it true or false? So the answer is true. So when you have crystalline domains in the polymers and you have a molecule, uh, you know, it may not be easy for the molecule to diffuse through this, crystalline domains, and this crystalline domains actually acts as an obstacle for the molecule to diffuse through. So the molecule has to take a much more longer path through the amorphous region to diffuse from this position to this position. So crystalline domains acts as an obstacle impeding diffusion of small molecules. Okay, next, data at higher temperature can be correlated to dash time in master curve. So this is based on the time temperature superposition principle, where you create master curve at particular temperature, uh, and you have tested samples at different temperatures, right, from very low to very high temperatures. So in that case, data what you get at very high temperatures, where will it go in the master curve? Whether it will go to a very short times or whether it will go to a very long times. So in master curves, the data obtained at higher temperatures uh, for particular set of time scales will go to a longer time in the master curve. So you could see, uh, you know, from this, master curve that is created for a creep compliance, the data that is obtained for a, hmm, very high temperature, very close to a viscous behavior, it goes to uh, very high time points, whereas a very low temperature, it goes to lower time points. Okay, which is you know closer to your elastic behavior. So very low temperature, the material does not have sufficient thermal energy to relax. Okay. Similarly, at very low time also a similar condition happens. Okay, and does not have sufficient time to relax. Okay, next. This is a problem. So a viscoelastic fluid is modeled as a spring and two dashpots, all connected in series. So the spring has elastic modulus G, and the fluids in two dashpots have viscosities eta 1 and eta 2. Okay. The constitutive equation for the fluid is, so the constitutive relation is between stress and strain. It's given actually stress and strain rate, that is what is given in the options, where the over dot actually represents the time derivative. So is it stress is equal to G into gamma plus eta 1 plus eta 2 into gamma dot, or is it stress is equal to G into gamma plus eta 1 minus eta 2 into gamma dot, or is it gamma dot is equal to sigma dot, your stress rate of change of stress with respect to time, your time derivative of stress, by G plus 1 by eta 1 plus 1 by eta 2 into sigma, or is it gamma dot is equal to sigma dot by G plus sigma by eta 1 plus eta 2? Which of these options is right? There's a second part of the question also. So in this second part, they've asked for a periodic stress, sigma is equal to sigma naught into e power I omega t. The strain will be given by, will it be given by gamma is equal to sigma naught into 1 by G plus I by omega into 1 by eta 1 plus 1 by eta 2 into e power I omega t, or is it strain is equal to sigma naught into 1 by g minus I by omega into 1 by eta 1 plus 1 by eta 2 into e power I omega t, and gamma is equal to sigma naught plus eta 1 plus eta 2 into omega I the whole multiplied by e power I omega t by g, or is it gamma is equal to sigma naught minus eta 1 plus eta 2 omega I into e power I omega t by g. So this is the GATE 2013 question. So they've given that a viscoelastic fluid is modeled as with mechanical analogs using a single spring and two dashpots which are connected in series. So spring and dashpots connected in series, spring having modulus G and dashpots having viscosity zeta 1 and eta 2. Okay. So for series combination, as we saw in the question number 1, for series combination, the stress across each element is same. So sigma of spring is equal to sigma of dashpot 1 is equal to sigma of dashpot 2, which is equal to the total stress. Okay. Whereas your strain across each element are different. So the total strain will be sum of strains of strain of spring plus strain of your dashpot 1 and dashpot 2. Now for spring, the strain can be obtained from the Hooke's law. Hooke's law states that stress is directly proportional to strain and the proportionality constant is your modulus. So if you just realign it, you will get strain is equal to stress by modulus. So sigma by G. Next for dashpot, you can arrive at strain rate is equal to sigma by eta. This is nothing but from your Newton's law of viscosity, where it states that your uh, stress is directly proportional to strain rate and the constant of proportionality is your viscosity. So rearranging it, you get strain rate is equal to stress by viscosity. So for dashpot 1, it will be sigma by eta 1, and for dashpot 2, gamma dot will be sigma by eta 2. So now we have the relation that gamma is equal to gamma s plus gamma d1 plus gamma d2. Now, if you differentiate on both sides, we get uh, d gamma by dt is equal to d gamma s by dt plus d gamma d1 by dt plus d gamma 2 by dt. Why are we actually differentiating is that we are trying to incorporate strain rate, because we have informations more on strain rate of dashpots than on strain as such. So gamma dot is equal to for spring, your gamma dot will be sigma dot by G. For dashpots, you have the direct relations plus sigma by eta 1 plus sigma by eta 2. So that is equal to, you will get your gamma dot is equal to sigma dot by G plus sigma into 1 by eta 1 plus 1 by eta 2, which is nothing but your option 3. This is what is your constitutive relation. Okay. For the viscoelastic, your fluid. Okay. You could see the option 3 for this viscoelastic fluid. Just gamma dot is equal to sigma dot by G plus sigma by eta 1 plus eta 2. Now the second part of the question is that a periodic stress is applied. So you have sigma is equal to sigma naught into e power I omega t. Okay. So your strain of spring becomes sigma by G, that is equal to sigma naught into e power I omega t by G. For the dashpot, it is gamma dot is equal to sigma by n, which is equal to sigma naught e power I omega t by n. So integrating the above equation, because the question asked is what will be the strain for the periodic stress applied. So for that, your dashpot strain rate relation should be converted to a strain relation. So for that, you are integrating the equation, because we have the differential form, we have to get the do the integration to get the strain. Okay, so gamma is equal to sigma naught by eta e power I omega t by I omega. So doing the mathematics, you will get, because your complex notation I is in the denominator, you're just making it in the numerator. So multiply and divide by I omega, you'll get minus I sigma naught by eta omega into e power I omega t. So gamma is equal to gamma s plus gamma d1 plus gamma d2. So we have the values of gamma s, gamma d1 and gamma d2. So that is equal to sigma naught e power I omega t by g plus minus of I into sigma naught by eta 1 omega e power I omega t plus minus I into sigma naught by eta 2 omega e power I omega t. So taking the common outs and all, you get gamma strain is equal to sigma naught into 1 by g minus I by omega into 1 by eta 1 plus 1 by eta 2 e power I omega t, which is nothing but your option 2. Okay, when a periodic stress is applied for this viscoelastic fluid element. Okay, viscoelastic fluid. Next question. Surface resistivity is related to volume resistivity, a material property. As is it related as surface resistivity is equal to volume resistivity into thickness, or is it surface resistivity is thickness divided by volume resistivity, or surface resistivity is 1 by volume resistivity into thickness, or is it surface resistivity is equal to volume resistivity by thickness? Which of these is a right relationship? The answer is surface resistivity is equal to volume resistivity by thickness, where thickness is the thin layer of surface through which the conduction actually occurs. Okay, thickness of the thin layer of surface through which the conduction occurs. Okay, so the surface resistivity is actually brought into picture because the surface, may not have similar behavior as the bulk. The surface may have some impurities or dust or moisture accumulation due to some defects or cracks present in it. So the resistivity might be quite different from your actual bulk of the material. That is why this concept of surface resistivity comes into picture. Whereas volume resistivity, which is nothing but a material property. Okay, next question. The water vapor transmission rate is a dash test while permeability is dash. So your water vapor transmission rate is actually a trait test, whereas permeability is a material parameter, material property, sorry. Okay, next. Critical stress at failure is related to crack length as, is it directly proportional to the crack length, or is it inversely proportional to the crack length, or is it directly proportional to the square of the crack length, or is inversely proportional to the square root of the crack length? How is critical stress at failure related to the crack length? It is actually it is actually inversely proportional to the square root of the crack length. So as you can see here, this is based on the Griffith's hypothesis. So your critical stress sigma c is equal to 2 times E into your surface parameter by pi c the whole power half. That means 1 by c power half. That is, it is inversely proportional to the square root of the crack length. Okay. So this can also be rewritten as E into GC by pi c, where GC is nothing but your work of fracture. So when and it is equal to 2 times of the surface parameter defining the surface and energy of this crack surface. Why is it 2 times? Because when one crack is formed, 2 surfaces are created. Okay, that is why. Next. Friction coefficient in body with synovial fluid is lower than friction coefficient on ice. Is it true or false? So ice, we know the surface of ice is very slippery, and when we try to walk on ice, we tend to slip. That means they have a very low friction coefficient, right? They do not have good amount of friction for us to stand comfortably, right? So is the friction coefficient of synovial fluid lower than friction coefficient of ice? It is actually lower than friction coefficient of ice. So the statement is true. So you can see that the friction coefficient of synovial fluid is of the value 0.002 to 0.0022 to 0.03, whereas for ice it is 0.02 to 0.05. You could see that the friction coefficient of synovial fluid is one order lower than that of the uh, friction coefficient on ice. That is why these synovial fluids are basically present in your joints and all. Okay, because in your joints, for example, in your hand, in your joints, you try to bend your arm and all, right? So in these places and all, your synovial fluid is present. In fact, in your legs, in the knees and all, synovial fluid is present. Okay, that is why you're able to comfortably move and there is no friction. Otherwise, if there is a friction, no, the bone starts, colliding with each other and they start, disintegrating and all. Okay, so this synovial fluid, it plays very vital role, and that is why you see in case of people with arthritis, right? What mainly happens, osteoarthritis, right? What mainly happens is that the synovial fluid content decreases. That is why, your bone starts colliding with each other and it starts disintegrating. Okay, there is a reduction in the bone density and all. It starts breaking and all. Okay, so your synovial fluid is such very important, lubricating material, and it can be an inspiration for creating lubricating materials for practical applications as well. Okay, because it is having very very low coefficient of friction. Addition of rubber particles to epoxy toughens the polymers, thereby increasing its resistance to fracture. Is it true or false? It is true. So rubber particles are added to epoxies to toughen them. So what happens when you add rubber particles? So you could see the data for unmodified epoxies and epoxy with rubber particles, about 5 pHr of rubber particles of size less than 5 micrometer. So you could see other parameters like heat, distortion, temperature, strength, strain and failure, modulus and all are of similar values, or there is a minor increase or decrease. But when you see fracture energy and isode impact strength, there's a one order increase in these two parameters when rubber particles are added. That means they resist the fracture, yeah, and toughens the polymers and resist the fracture. Okay, they take up the load of impact and fracture, and they tend to have some conformational changes. These particles, they take up those things and toughens the polymers, and helps in increasing the fracture energy and impact strength of these materials. Okay, next, polymeric fiber interfaces in polymer fiber composites can have different alignment or chain conformation of macromolecules compared to that of macromolecular chain far away from the interface. Is it true or is it false? It is actually true. So in interface between the uh, fiber and the polymer, as you could see, this is a long fiber and a polymer. So the chains can orient along with the fiber in fiber directions. They can orient. Okay, compared to a more coiled structure, as you can see here. Okay, so there is definitely a possibility and happening that at polymeric interfaces, there can be a chain conformation difference compared to that of the bulk phase. Okay, that's all with the session. Thank you. Hope you're clear. So thank you. Thank you all for the session. Have a nice weekend.